Okay, greetings everybody. Sorry I can't be with you in person this morning, but I'm going to tell you a lot about two algorithms today. Okay, greetings everybody. Welcome to Bayes. So this is a virtual edition, no in person today. Hopefully we can make this relatively short. So I'm going to tell you about two algorithms today, and both algorithms are used for sampling from some distribution. This is an extremely important thing to do. So if you have a distribution, so I'm kind of just thinking something, maybe it's weird, and this might be multi-dimensional. We'll talk about this in a multi-dimensional setting. But you just have some distribution. Okay, so I'm just drawing it out as though it's maybe one-dimensional. So this would be pi theta. Given your data, this is your posterior and theta. And so basically I want to go in here and I want to grab points with frequency relative to the area under the curve. So let's imagine that this part of the curve has, say, 20% of the area under the curve. So it integrates to 0.2, densities integrate to 1. Then it means that I want to grab samples in this interval 20% of the time. And I want to do that at a very refined level. So I don't want it quite this coarse, but I want to be able to basically estimate where are these peaks, and if I can understand that shape, if I plot a histogram of all of my samples, it will resemble that shape. Then I can understand everything there is about that distribution. So for example, maybe I want to compute means or variances. I can use empirical estimates to do that. I can use my samples to compute interval estimates. Theoretically, I could use my samples to compute modes of that density. There's adaptations to what I'm going to tell you today that people use for multimodal cases. If they're trying to find maximums, you can build that into the algorithm as well. But the fundamental building block is to sample from this distribution. And so I might be thinking about theta as high dimensional. And so doing all these high dimensional integrals would be very challenging. And in general, if I develop this posterior using maybe some complex physics, hierarchical modeling, doing those integrals might not be feasible. So that's kind of one of the limitations to Bayesian statistics is you have to do a lot of calculus. These algorithms that I'm going to present to you are going to alleviate the need to do all of that calculus. And so if you're trying to estimate something, no closed form solutions exist. Some of you might know about quadrature techniques, Riemann sums, for example, or Simpson's method. This would be a competitor to that. It's a different approach for understanding the shape of this function through an approximation. We'll talk more about that next time. So we want to sample from our stuff. So again, maybe we can write down this density function is a likelihood function given x, pi theta, my prior. And so I might have judicious reasons for picking my prior, and I've modeled the data so I can induce the likelihood. So I can write down these two things. I'll point out very typically in sampling schemes, you do not need the denominator of this. So you do not need to compute this. We'll talk about that more next week as well. I'll say a few things about it at the end of this lecture. I'll try not to tell you everything. So this right here down in the denominator is just another way to write the margin of the data. And this is a constant, so all of the shape is informed through those two functions, the prior distribution and the likelihood. So name of the game is sample. So Bayesians for a long time, they were talking about good reasons to come up with priors. They were discussing things like the likelihood principle, and it's the only way to do statistics, and they kind of built this philosophical paradigm. I think it's really these sampling schemes that kind of changed everybody's mind. So I think once you can actually do the stuff that you're talking about, it becomes a real utility. So back in the 60s, 70s, even into the 80s, people often weren't able to compute this distribution. So if it were a high dimensional distribution. So maybe if there were 10 parameters or something like that in this model, it would be very hard to do all the calculus. And so people turned to other methods. It's once we started to understand these samplers, and these come about in the 1990s. So this is the one that came out in 1990, and then there was a whole slew of algorithms that came out. Some of you will realize that these algorithms weren't entirely new, but their generalizations were new in the 1990s. So basically, computers changed everything for Bayesians. You could sample from these distributions through these various algorithms. You could compute anything you wanted, so long as you had enough computational horsepower. At universities, we tend to have enough computational horsepower. So there are some new methods that have come into play. But I would say these are full-blown methods. They give you what the whole distribution looks like. There's approximate methods, variational methods that you're just doing maximization, and that's kind of a different branch to all of this. So these aren't always the most efficient ways to do your inference, but they give you everything. Sometimes they might give you a little bit too much. But I would say regardless of maybe their computational potentially inefficiencies, they're very useful. So long as you're willing to wait for your answer, maybe a few hours, maybe a few weeks, maybe a couple months in the worst case, these algorithms will be very good. We're going to be addressing all of those issues next week. Okay, so our goal is to sample from our posterior distribution. And we can write this down. So I'm kind of presupposing you're able to evaluate this function right here. So in the numerator. So you give me a theta, I can plug it into that function, and I can evaluate it. I don't need to evaluate the denominator, but evaluating this function and being able to sample from it are entirely different things. So usually we can evaluate the function, but we don't know how to directly sample. These methods will help us to do that. There are some methods out there for like normal distributions. You wouldn't run a Gibbs sampler on a normal distribution because there's more efficient ways to sample from that distribution. So there's direct transformation methods, perfect samplers, and if you can use those, you probably wouldn't want to go down this path of Gibbs or Metropolis Hastings. These are general purpose samplers. So if I can just evaluate the function, and there are branches of MCMC that you don't even have to evaluate the function. It's kind of interesting. We're not going to talk about that in this class, but maybe down the line. These are general purpose samplers. So, the idea is I can build some very strange model for some scientist or engineer, and then basically I need to be able to draw samples from that model. We'll go into more details next week when we look at the original Gelfand and Smith problem that helped motivate the original Gibbs sampler. So I want to just jump into these two things and tell you what the algorithms are. But first, let me just tell you what MCMC stands for. This is Markov. This is chain. This is Monte Carlo. Should probably change this a little bit. So I could actually do a little c right here and a capital N. This is Monte Carlo. With my capitals, I'm just denoting what are actual proper nouns. So this is a place, Monte Carlo. Markov is a person, and this is the same property that you would learn in probability class, where the probability distribution only depends on the previous value. That's the Markov property. It doesn't depend on values past the last step. We'll talk about that. Chain is not part of a proper noun, so you don't need to capitalize that. You'll see this written out different ways. Sometimes you'll see that capitalized, but definitely if you're going to capitalize things, these need to be capitalized. Just as a side note, Monte Carlo, this comes about through the place, Monte Carlo. So if you've ever been to basically the boundary of France and Italy, there is a country called Monaco. And in Monaco, they have a town called Monte Carlo. And so there's a lot of big casinos there. There's an F1 racetrack there. But the people that were creating these algorithms, they understood random processes, but didn't want to speak to the world through a mathematical language, and casinos represent some sort of a random process. And that's where the name is derived. We'll talk about the Markov property in these algorithms. Both build Markov chains that converge to sampling from this distribution. So I should point out that your first draws are likely not to come from this distribution, but rather this is an iterative algorithm where the samples will converge to the correct distribution. We'll talk about all that next week when I actually implement this for you and show you examples. But I want to present you with the algorithms, so as you're going through your homework, you kind of know what I'm asking you, what you're going to have to do. Okay, let me just write down both algorithms. You might be thinking to yourself, why do I need to learn two algorithms? Why can't you just tell me the best one to use? It depends on the cases. I will point out that Gibbs sampling is a subset of Metropolis Hastings. So let me just say this, and we'll prove this later on. So note, Gibbs is a type of Metropolis Hastings. So I'm going to start writing MH. This is Metropolis. And this is Hastings. These are both people that contributed to the formation of these algorithms. So Metropolis came up with a version of the algorithm, I think, in 54, and Hastings modified the algorithm in 57. I'm going to talk about the Metropolis-Hastings algorithm and not just the Metropolis algorithm, because Metropolis is a subset of Metropolis-Hastings. We'll clarify that after I write down what the algorithm is. So we'll prove this later. So this isn't obvious. We'll go through, I think, enough of the theory to demonstrate that this is true. So don't worry if you don't see that automatically. I think in 1994, when Luke Tinnery ended up writing his kind of overview paper on all of these algorithms, showed all the connections between the algorithms. So it took a while for people to understand this. I grew up in a generation where this was fairly obvious because it was written down in textbooks, as it is now. But back in the early 90s, I think people were working through these connections. Okay, so let me write down what a Gibbs sampler is. First, I'm going to write down our goal. And I'm going to say sample. From pi theta. Now I should point out, we could sample from any distribution. These are general purpose samplers. So if you can write down the kernel of the distribution, which for Bayesian is represented through the likelihood times the prior, if you can write down that kernel, you can apply these algorithms. So they don't have to be posteriors. It's just that Bayesians are always operating off of this probability distribution, and they're doing inference on the random variable that they've upgraded to a random variable through Bayes' theorem. So they turn everything into a probability distribution, sample, and then report their inferences. So a lot of Bayesians spend a lot of time building models, but they probably spend more time on implementing those models and doing the computation. So we want to sample from this. And I'm going to make it a little bit challenging. I'm going to say this is three-dimensional. So I'm going to say theta, so this is a vector, and maybe I'll call that cap theta. So this is my capitalized theta. Some people think it looks like a circle with an H in the middle, but that's cap theta. So I can't help myself. Since I'm going to make this a vector, I need to make it capitalized. And I'm going to give you names for these three variables. I'll call them theta 1, theta 2, and theta 3. So three-dimensional distribution. I don't think we've touched a 3D distribution yet. We've certainly seen two-dimensional distributions. In the normal case, two parameters, the mean and the variance, jointly infer them. And that's the example I'm going to kick us off with on Monday. So we ask you to do that on your homework as well, but I'll demonstrate several things I'm going to allude to in this mini lecture. Okay, so here's what a Gibbs sampler does. So Gibbs breaks up the full conditional. So Gibbs sampling. And this is going to run in a for loop. Again, this is an iterative algorithm. So for, I'm going to give myself just a little bit of room right here. There's a couple steps. But my first step is going to be to initialize. All iterative algorithms need to start somewhere, so I'll initialize in a moment. I'll pick an index, I'll call it t, and this is going to go from 1 to some large number, and I'm going to call that cap t. Every time I open a for loop, I close it immediately. Okay, so this is some big number. Those of you that have run iterative algorithms, there's always the question, how big should this be? And what I'm going to say is it should be big enough. So meaning that if I keep running it, I don't find a different solution. Basically, everything becomes stationary. And we'll talk about the definition of stationarity later, but basically, everything should converge. My samples should look like whatever the distribution is. So as long as it does that, it measures the tails properly, the modes properly, the troughs in between the modes, and it doesn't keep changing, then I'll say that it's converged. We need a little bit more guidance on what that means. We'll talk about that next week as well. Here's what a Gibbs sampler will do. Is it's going to sample first theta 1, and it's going to do it from its full conditional distribution. And I'll just put an index on here, t. So theta 1, and later on I'm going to sample theta 2. I'll tell you about that second. And rightfully, I'll tell you about theta 3 third. There's a little nuance difference in all of these. So basically, we're going to sample from 3 different univariate distributions. So there are generalizations to this, but I'm just going to write this down like this. Pi theta 1, this is going to be given my data, so everything's conditional on my data as a Bayesian, so I'm just using this as notation. So x is always going to be fixed in there. Everything is conditional on data. But if this was just a general distribution, you could remove x and not be thinking about it as a Bayesian might. So, and I'm going to sample it from x, and it's also going to be conditional on theta 2 and theta 3. So, and I said I needed to initialize everything. I have to have a theta 2 and a theta 3 to plug in here. And so I'm going to plug in my previous draws. T minus 1. So what I need to do before I kick this algorithm off is I need to initialize those 2 values. So in general, if you're updating 3 full conditionals, you'll need to initialize 2 things. More generally, if you're sampling from k full conditionals, you'll need to initialize k minus 1 things. So I need to initialize first. So I'm going to set theta 2, 0. So I'm indexing starting at 1, so t minus 1 is 0. This is just going to be some number. And I'll call it whatever number it is. You pick a number. If you know about where it's centered, you should plug that number in. Theoretically, we should be able to start from anywhere, and this algorithm will work itself out. So in the worst case situation, you have no idea what these parameters will be. And I think that your algorithm should be robust to that setting, because that's usually where I'm at. So you'll initialize this to some other number. I'll call it pound prime. So you just pick some numbers in here. So I'm kind of imagining these are scalars. And so I'm just going to pick 2 numbers. Maybe that's a 5. Maybe that's a 2. So as long as those are in the support of that random variable, we'll consider it good enough for now. So this right here is the full conditional. This is a word that we've seen before. Now we're going to start using this word for theta 1. Very typically, people will give you some notation for this. They'll get tired of writing all this out. And so in papers, it's very common to see this written, aka pi theta 1 given bar. So in a journal manuscript, you're likely to encounter this notation. So this is the full conditional for theta 1. It's just saying theta 1 conditioned on everything else in the model. In our model, we've got our data, and we've got 3 parameters, so I'm going to condition on all the other parameters. Okay, so Gibbs Sampler updates these other parameters similarly. So we're going to sample from pi 2's full conditional, theta 2, sorry. Theta 2's full conditional, everything's conditional on the data. This is going to be conditional on theta 1 and theta 3. Question is which theta 1 and theta 3 do I plug in? I'm going to keep my previous draw there. That comes from my initializer because I haven't updated theta 3 yet. But I just updated theta 1. And so I'm going to plug that one in. So I'm going to take this value that I just got out of here, and I'm going to plug it in there. Theta 3 is coming from that initial condition. Theta 2 is being updated. Similarly, I'm going to sample theta 3 from its full conditional. So this is going to be conditioned on theta 1 and theta 2. Which values of this do I plug in? This is going to be t, and this is going to be t. So this same value is going to get repropagated here, and then this value that I just updated, it's going to be updated there. So Gibbs Sampler just iteratively samples from the full conditionals in the model. There are a lot of details to talk about here. How you pick the blocks, how you break things up, and it all matters. So I don't want to say that nothing matters. Theoretically, if I weren't concerned about how long I run this thing for, everything will work. So the only thing that we're going to squabble about is how long it takes for the algorithm to converge. So lots of issues to talk about there. This is a Gibbs sampler. So if I ask you to write down a Gibbs sampler, you just need to write down the full conditionals of the model. So we'll be studying this problem from Gelfand and Smith later next week. They describe the full conditionals, but you have full conditionals on mean vectors, and you have full conditional on covariant structures as well. And so I need to teach you a little bit about probability distributions for matrices, but in that problem, they're going to iteratively sample from full conditionals. So Gelfand and Smith they figured out this would work and it would converge to the joint posterior of all the parameters they were trying to learn in their model. And then they ended up writing a paper for JASA that described all the mathematics behind everything. So they actually first published the paper where they were doing an application, and then they came out with their hard-hitting paper with all of their theoretical details. And I'm going to teach you most of that next week. Okay, that's Gibbs sampling. So break up the fault conditionals, work them out. So I can give you an example, just real quickly. This is the one you're going to be doing on your homework. And I ask you to do this a couple different ways. I ask you to do it via Metropolis, and I ask you to do it via Gibbs, and I think I even asked you to do a combination between these two algorithms. So these algorithms have the same theory that dictates them, because they're really kind of the same algorithms. I'll tell you about Metropolis-Hastings in a moment, but these algorithms are combinable. I'll tell you a little bit about it. The presupposition right here is that I know how to sample from all these distributions. So I might not know how to sample from the joint, but I do know how to sample from maybe their full conditional distributions. So an example. So I'm going to say xi's come from a normal, and it's got two parameters that I want to learn, mu and phi. And phi is my precision parameter. So hopefully we're at a point where we like the precision because we like gamma distributions. There's no other reason. I goes from 1 to n, everything is IID. I can work out the full conditionals. So the full conditionals, you can implement this after I tell you about it. These are going to be pi mu, given x, in phi, and pi phi, given x, in mu. I think we worked these out before. So this is going to be a normal distribution. It's going to have parameters, x bar, and it's going to have variance parameter. This is going to be 1 over phi n. So this right here is 1 over sigma squared, just so you can get your bearings straight. And this right here is sigma squared over n. So they mean the same things. And this one we worked out before. This is a gamma. And it's got two parameters. This is n over 2. And this other one is going to be the sum of squared residuals from mu, squared over 2. Both of these distributions, you have some indication of how to sample from them. You can go to R or MATLAB, but there's different implementations. They have perfect samplers, and they'll know how to sample from this. Usually use something like a Box-Mueller algorithm right here. I'm not going to teach that to you, but if you ever want to see what it is, ask me in office hours, and I might tell you. Gamma distribution, we also know how to sample from that. So I asked you in the previous homework, and I ended up removing that question. I asked you to sample from the joint distribution of mu and phi, but several of you were alert enough to know that you don't know how to do it. You can implement a Gibbs sampler for this. So let's do that. So this is just going to look like this. For t goes from 1 to cap t. I'm going to sample mu t. It's going to come from a normal with mean x bar. So usually I pre-compute x bar and I only evaluate it once in my code. I store it and I always use it. I plug it in right there. And then I take 1 over phi t minus 1 over n, and I plug that in. So what I need to do first is I need to initialize this. So phi 0 is going to be some number. I better make this positive. If I picked a negative number, my sampler would not perform correctly. If you try to plug this into a normal distribution and try to sample it, you would get an error message instantly. So I better make this something positive. So I'll just pick some number, plug it in, and make sure it's in the support. Precisions are positive, variances are positive, standard deviations are positive. I better pick something positive. Then I'm going to take phi t and I'm going to sample it from this gamma. N over 2. Unfortunately, I'm going to have to compute this every time. So you could break this into the sum of squares if you wanted to and make some easier calculations. So you could make it so you don't have to evaluate everything every single time. But I'm going to take this previous draw that I just got, squared, and I'm going to divide by 2. End. I'm going to run this for a long time. So, turns out this converges very fast. I'll be illustrating something. I'm going to try to use some of what I know about samplers to play my sampler so you can see what some of the issues are. This is probably a bad example to start with simply because it converges really well. So it works too good. You'll see that when you implement this for your homework. So I'll just make a note. Eventually, not right away. I think in this sampler it takes 2 or 3 iterations for it to converge, so it converges almost instantly. Some samplers will take thousands of iterations to converge, if not more than that. Eventually, at some point, I'm going to write this down, is theta b. I'll tell you what that stands for in a second. Let me just write this down. So I get these 2 sets of samples. Mu, I'll write it down, b, phi b. These pairs, mu b plus 1, phi b plus 1. Once it converges, it stays converged. We have theory on that. This converges in the strongest sense, so it should never jump away from what appears to be converged, if it's running properly. Dot, 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 out to mu. T is my last iteration of this algorithm. Phi t. Our samples. From the joint. Pi, mu, phi, given all of my data. So this is called the burn-in period. So this right here is called burn-in. So whatever that number is, you have to monitor some diagnostics and look at these Markov chains running. But the first iteration usually isn't converged. After a while, this thing converges and then it stays converged. So what you do is you take all of your old samples, 1 through b minus 1, and you throw them away. Usually people aren't looking for the exact moment of burn-in, they just want to make sure that they've gone far enough into the chain. It'd be a really difficult theoretical exercise to work through for any general problem to say what's the minimum burn-in period. So any burn-in period, so long as it's enough, and then you collect enough samples to represent your distribution, are going to be fine. Lots of practical issues there. Okay, the presupposition in a Gibbs sampler is that I know how to sample from the full conditionals. Metropolis-Hastings helps us when we don't know how to do that. So I'm going to write down what Metropolis is. I'm going to show 2 different variants. And I should mention, when I say Metropolis, I mean Metropolis-Hastings. Most people will mean that. Let me write down what Metropolis-Hastings is. This is a very influential algorithm. This is what I consider the saving grace for Bayesians, computers, Metropolis-Hastings type algorithms. So, again, the goal is to sample from pi theta given x. You can be thinking about this as three-dimensional. This will come up in the future. Theta 1, theta 2, theta 3. For our first algorithm that I'm going to show you, I'm just going to leave it in this notation, and I'm going to update everything together. So this is Metropolis-Hastings. So step 0, initialize. I'm just going to write it down as a block. This is going to be everything. That's just going to be theta 1, theta 2 at the 0th iteration, and theta 3. So in this first implementation I'm going to show you, I'm just treating this as just a collection of things all together. I've got some notation for it. Later on, we can combine the concepts in these algorithms. So this is what it looks like. For t goes from 1 to some large number. Again, we're going to need to converge to what's called stationarity. Our chain needs to limit to something. We're going to be running the limiting distribution, and through a few properties I'll introduce you to that I'll call ergodicity, this thing is guaranteed to converge eventually. I need to tell you about more details. So here's just a two-step process. 1, 2, and there is kind of a third step, but it's just your storage step. Lots of details in this first step that I'm not going to cover right now, but through the homework and lecture next week, we'll be covering a lot of cases. I need to propose something. So I'm going to call this theta star. This is the whole vector. I'm going to write this in as using blue just to denote its importance. This is going to be g theta. And this is going to be conditioned on where I was last time. So this is my initial draw at the first step. This is called the proposal distribution. This is the most important thing in MCMC algorithms. This is the whole question, is how you pick it. Which proposal, why? And so for problems that come up over and over again, people have come up with some really good strategies for this. Then there's some general purpose stuff that is more computationally expensive, but it's more adaptable to complex problems. So proposal. This needs to propose into the support where theta lives. So I'll just make a note. This needs the same support as pi, our target. Ultimately, we're going to be either going to where we proposed or we're going to stay in the same location. There's one of two possibilities. I'll write that down in a second. The second step is the Metropolis-Hastings decision rule. So once you have your proposal, everything else is automated for you. So the question is how do you come up with a good proposal? Lots of issues for next week. So then we're going to try to accept. So I'm going to write down an acceptance probability. My acceptance probability, I'm going to give us some notation. This is going to be theta star given theta t minus 1. And this is going to be an acceptance probability. I'm going to flip a coin in a second and decide where to move to. So, acceptance probability. So before completing the algorithm and telling you what this rule is, we're going to propose something, then I'm going to compute some probability. This is going to be a number that lives between 0 and 1, because it's a probability. So alpha is an element of this. So what I'm denoting right here is this is the acceptance probability of moving from where I previously was to the proposed location. So I'm going to have this magic coin that I compute in every step of this algorithm, and I'm going to flip that coin exactly once. And if it lands heads, I'm going to move to where I proposed. If it lands tails, I'm going to stay at the same location. And we're just going to keep doing that over and over and over again. This algorithm will converge to sampling from the correct distribution. Now the magic part is getting the coin so that these coin flips, basically Bernoulli draws effectively, has the rule such that this thing converges to the right distribution. So here's the magic rule. This is going to be minimum of 1 in something else. And I'm going to give myself a little bit more room in a second. And I'm going to write what that thing is. So let's just leave this as a big surprise. I'll call this the MH decision rule. Fortunately, somebody broke the whiteboard that I keep trying to walk over to, and so I only have this small whiteboard for right now. Sorry about that. MH decision rule. I'll tell you what this is in a second. The third step is just flip the coin and make the move. And so I'm just going to say theta t, this is what I'm updating. This is where I'm moving to at my next iteration. This is going to be one of two things. This is either going to be theta star. I'm going to make all these caps. Or I'm going to move to theta t minus 1. I'm going to stay in the same location. So some of you might be familiar with accept rejection algorithms, where you either take the sampler or you throw it away. This is not that. This isn't accept reject. This is you're always carrying the sample with you. So you accept the proposal or you stay in the same location. We'll talk about the implications of all of that next week. So this is going to happen with probability. Alpha, theta star, given theta t minus 1. And this is going to happen with probability 1 minus alpha. This is just notation for a probability. This is a coin flip. So I'm going to take a Bernoulli and I'm going to flip it with this probability. If I see a 1, I'm going to move to theta star. If I see a 0, I'm going to stay in the same location. And I'm going to store all of those values. I need to tell you the Metropolis decision rule, but this is going to have the same property as in Gibbs sampling, that eventually, after some period, and we still use the same terminology, the burn-in period, these samples will converge to everything. So let me show you what the rule is. So this is what I plug in right here. So there's going to be a valuation of a function that I plug in here. It's going to be some number. It's going to be a positive number. And it can be greater than 1. And if it is greater than 1, then the minimum between 1 and something greater than 1 is 1, and I'm necessarily going to accept the move. I'm going to talk about the meaning behind that next week when I have you in person. So this is what it looks like. The MH decision rule. So this thing is this. I'm going to take pi theta star, give it x. I'm going to divide it by pi theta t minus 1, give it x. Then I'm going to have something else. This is going to be g theta star, given theta t minus 1. This is my proposed density. This is g theta t minus 1, given theta star. So I want to just point out, in step 1, we're sampling from this distribution. So your proposal has to be something you know how to sample from. So we'll talk about all the implications next time. So this is an evaluation step. So this I'm sampling from. I've got a magic button on my computer. I can draw samples from it. This is an evaluation. I can evaluate the density function right here. So I want to point out that this part right here, in a Bayesian context, I don't need to write out the normalizing constants. This is equivalent to the likelihood star given x times pi theta star divided by the likelihood function in our previous time step times the prior evaluated at the previous time step. So the Metropolis decision rule requires you to do some evaluations, but that's to be distinguished from sampling, which is very different. I could write this out exactly and write down the margin of the data. I usually end up writing down some integral. Right here, I'll do it long-winded. Integral likelihood theta given x, pi theta d theta. There would be one down here as well. Integral likelihood theta given x, pi theta d theta. There's something beautiful here. These cancel. So I don't actually need to evaluate the posterior. I just need to plug in likelihood times prior to be able to evaluate them. Again, there are variants of this algorithm where you don't have to do the evaluation. I could fill a whole class with variants of this algorithm and variants of G and discuss all of their properties. So somebody that studies Markov chain Monte Carlo for a living, which is where I cut my teeth in statistics. What got me into everything is these algorithms. It's all kinds of mathematical issues as to why you pick these computational and mathematical issues simultaneously. So there's a whole wealth of theory on this. So let me just recap. We want to sample from this distribution. What I can do, if I don't know how to sample from that distribution, is I can sample from some proposal that at least has the same support. So if I had something like a, something on between negative infinity and infinity, maybe I could use some sort of a Cauchy distribution there, or maybe some sort of a normal distribution. So it lives in that same support. If I had something positive that I were trying to sample from, then maybe I'd use maybe a gamma distribution or a truncated normal distribution. And I'm going to give you several references on that and ask you several questions in your homework. But this is the whole question. Which G, how well does it work? Then I just compute this probability. So I take the minimum of 1 with whatever this number is. I don't have to compute the normalizing constant in the posterior because it cancels. I'm going to compute whatever this number is. I'm going to plug it in there. I'm going to make this evaluation. That's my probability. Then I'm going to flip a coin with that probability. If that coin lands heads, I go to the proposed location. Otherwise, I stay where I'm at. There's a lot of fun things to talk about in these algorithms. So this is what you can do if you don't know how to sample from something. So let me just go back to Gibbs sampling, and I'm going to just tie this together. What you can do with both of them. I'm not proving anything yet. I haven't proved that this algorithm works. I haven't even told you why it kind of intuitively makes sense. And I certainly haven't done any math. I've just shown you what the algos are. The nice thing is you don't necessarily need to know why it works to operate it. If you can just compute this rule and do this, it will converge. Knowing the theory is going to help you when you program a bug into everything. So understanding what it should do and what it shouldn't do. Okay, so back to Gibbs, just real quick. Gibbs I won't write out all the gory details, but I ended up saying you break everything into the full conditionals. You run that into a for loop. So this might be theta 1, it comes from its full conditional. I'm going to use my shorthand notation, knowing that I'm plugging in previous draws into there. Theta 2 comes from this. Theta 3 comes from its full conditional. Now again, I'm just using shorthanded notation. I'm plugging things in here as I did when I wrote it down before. It just gets cumbersome to write the exact same thing. I presupposed you know how to sample from these. If you do, then you can just operate this sampler and the thing will converge. If you don't, you can bury Metropolis-Hastings steps in right here. So say I don't know how to sample from this. What I can do is I can do a Metropolis-Hastings step. So the solution is to add a Metropolis-Hastings step. So what I mean by that is instead of just saying I can do it, I build the MH step in directly. So I'm going to take theta 1 star. I'm going to get it from some proposal, has to live in the same support. This depends only on the previous draw. It has the Markov property. And then I'm going to do my decision, alpha. And I'm just going to shorthand it and write it down as alpha. But this is the transition probability of moving from where I previously was to accepting the proposal. Minimum 1. And now I just build that full conditional in right here. So this is going to be pi theta 1 star, given everything else, over pi theta 1 t minus 1, given everything else. So they're all conditional on the same thing. And then I'm going to multiply by, I'll just point out, these things are flipped upside down relative to the target. So the proposal is an inverse ratio. Theta t minus 1, g theta t minus 1, given theta star 1. So this is just this proposal function, and then I would close everything out. So it's this, the ratio of targets, that's what I'm trying to sample from. It's its full conditional, and this is the inverse ratio proposals. That's the Metropolis-Hastings decision rule applied to the full conditional. So these two things are multiplied together. So I'm producting them. Sorry for putting it on two different lines. So this ratio times this ratio. So this is the target ratio. It has theta star up in the numerator, t minus 1 in the denominator. The proposal's flipped upside down. It has the proposal down here and the target there. And I'm going to come back and I'm going to tell you why this intuitively makes sense next time on Monday when I have you in person. So let me just recap by saying if you did not know how to implement your Gibbs sampler, you could write down what the forms of the full conditionals were. Maybe this one you know how to sample from directly. Maybe this one you know how to sample from directly, but you don't know how to do this one. And so what you can do is you can pick some proposal that lives in the same support as theta 1. So if this was a positive variable right here, that needs to be positive as well. So if this is positive, that needs to be positive. So if this was, for instance, something that was across the whole real number line, and I only proposed values that were positive, I would never see the negative values. So I would be truncating those out, and that would be a problem. So I sample something that at least could be a candidate for that value. I need a random mechanism for doing it. This is the whole question in Metropolis-Hastings, is how you choose. I compute my acceptance probability, and then step 3, I choose whether or not to accept. So theta 1t is going to be one of two things. It's going to be theta 1 star, or where I was last time. So we don't discard anything, we keep it. So this happens with prob alpha, and this happens with probability 1 minus alpha. So you can combine these two algorithms together. They're both Markov chains, and their mixing properties are the same. Their speed of mixing, however, can be different, and that's okay. So we'll come back next time. We'll go through more details. I'll implement one of these for you, show you some practical issues. Lots of numerical stuff that you need to be aware of. But I think for maybe the rat problem on the homework, you can get started and just start thinking about some of the full conditionals. I'll be giving you a lecture on that as well. For Metropolis, maybe you want to give it a shot and see if you can update things jointly. If you can't update things jointly, maybe you can separate into the full conditionals and sample those. So if you have some time, knock yourself out, have a good time playing around with these. Otherwise, I'll see you next week and show you how to do more. Thanks, you guys.